Thank you so much, everyone, for joining. Today, we will talk about thermal analysis of passive cooling for LED systems, and I'm very delighted to see so many of you joining our webinar for today. Let us jump straight to the agenda. So the webinar will be split into 4 parts. In the first part, I will give you an introduction to SimScale, to the platform and what we actually do. And the second and the third step, we will talk about the case study, and my colleague Matt Bemis will give you a demo about our case. And in the last part, we will have a relaxed Q&A session where you can ask your questions. So if you have any questions during the webinar, please put them in the question field, and we will make sure to cover them at the end of the session. I'm the host for today's session. My name is Yusuf. I'm a product marketing engineer here at SimScale, and I'm a mechanical engineer by training. And I'm joined by Matt Bemis. If you want, you can introduce yourself.
Thank you, Yusuf. Like Yusuf mentioned, my name is Matt Bemis. I'm an application engineer with SimScale. I've worked here for close to 3 years. I've worked for a couple of simulation companies, CAD companies, and really am sort of a jack of all trades with CFD. So thank you for having me, Yusuf. And back over to you.
Pleasure to have you. Thanks, Matt. So let us talk about who we actually are. We are a SaaS company founded in 2012 in Munich, and SimScale goal is to empower every engineer to innovate products faster by making high-fidelity engineering simulation truly accessible from everywhere in the world. Our headquarters is in Munich, but we also have offices in Boston as well as New York. We have around more than 80 employees across 8 different time zones, and we have over 160,000 users worldwide. And with more than 300,000 simulation projects, we are the go-to platform for engineering simulation. We created the world's first cloud-based engineering simulation platform, and what you can do with SimScale is simulate cases in the field of fluid dynamics, so computational fluid dynamics, FEA, so structural mechanics, as well as thermodynamics applications. The only thing that you need is an account and a browser, because everything is basically accessible via a standard web browser. Let me quickly talk about the problems of traditional simulation tools. Usually these come with very high fixed costs, so that can add up to a 5 or 6 digit number. And you even have to prove the added value of these simulation tools or workstations before you can even prove the added benefit. What comes with this is that the workstations you acquire often need special hardware. This also comes with software installation required and also a lot of maintenance costs and work. A big disadvantage of this is as well that it's often or most of the time built for specialists. So what you need is a special training for these software tools and a lot of experience. The last disadvantage on this list is that the computation time often takes days or even weeks to finish. So why should you care about simulation in the first place? So what this graph or this plot shows you is that the more we move forward in the product development process, so in the first step we have the ideation phase, the concept phase, then the realization phase and the validation phase, is that the more we move forward, the more defined our product becomes, but the more harder it gets to actually make changes on the product, because they will get way more expensive over time. So what we have to do is use IT solutions in the early design phase, and this is what SimScale enables you. So you use SimScale in the early design stages or even in the ideation phase to test different designs. And I'll show you in a few seconds what this actually means. Let us quickly talk about the benefits of using SimScale. So as I've mentioned, you need often 5 to 6 digit number investment before you can even prove the added benefit of other simulation packages. This is not necessary with SimScale. So you can create an account, get started with SimScale, upload your CAD model, and basically can get started. There is no installation required or maintenance. The only thing you need is an account, a decent internet connection, and a browser. Therefore, it's very easy to set up. And what is very, very interesting is the seamless collaboration feature. So what you can do is you can share projects with your colleagues, so inside of your team, outside of your team, which makes it very, very easy to collaborate with other people. And what I'm very proud of is, of course, our world-class support. So if you have any questions regarding electronics cooling application or any other applications that you would like to simulate on our platform, my colleagues are here to help you. Last but not least, the computation time, which can be taken from weeks or days, as I mentioned, to minutes, to literally minutes. So, and what is even the benefit of using simulation per se? What we can achieve with simulation in the early design phase is that we can have an optimized design. Therefore, we can have fewer physical prototypes that we need. So we save a lot of time and therefore money. That comes also with a significant cost reduction in the product development process itself. What we can do with simulation, which is very, very convenient, is that we can simulate what-if scenarios. So you can have different designs on your SimScale account on the platform, compare them and really see how they perform or how they would perform in real life. And what comes with these benefits is that you can transition faster to the market. Right, let me summarize this. So traditional design process look as follows. So we have the design phase in the early stage, usually followed by physical testing, which really takes often weeks, and then you would go to production. However, how you can leverage this with SimScale or this SimScale tool is that you can significantly reduce the physical testing time by front-loading your simulations with SimScale, which results in this delta, which basically saves you more time, thus more money. This is kind of summarized here in this neat table. So what we would like to compare is the physical testing scenario with in-house simulation tools and SimScale. And what you can see that the number of design iterations goes from a few, when we talk about physical testing, to several tens of simulations when we talk about workstations. And really, when we talk about SimScale, basically unlimited amount of design iterations, and everything runs in parallel thanks to HPC systems that we use. And this takes us from turnaround times from days to weeks to literally hours for all of your iterations. And more significantly, the costs drastically reduce. So when you have like hundreds or thousands of dollars for a physical prototype, this can be reduced to tens or hundreds of euros by using SimScale.
So I'd like to first provide an overview of what types of capabilities SimScale has. So it is considered a multi-purpose or workbench type tool that has all the CFD physics you may see in a traditional desktop solution. So this includes both natural and forced convection, air or liquid cooling. We can model fans. We do support more sort of niche applications for electronics. For instance, we support anisotropic materials for PCBs to capture the thermal conductivity of the copper layers. And we do have idealizations like thermal layer resistances, as well as thermal resistance networks, where you define a temperature delta per watt. These are a few examples of some mostly forced convection scenarios which have been run in SimScale. Now, these are some nice looking images. I do like taking a look at them. However, all of them, you can just open a project, take a look at it. And if you're interested in how it runs, and if you have a SimScale account, you can take a look at the project, copy it, make some changes, and really dig into the details. I do think that is one big advantage I really like with SimScale. The lower ones here are some water-cooled applications. This is becoming a bit more popular as power density just increases. It becomes necessary to use cold plates and other things because other methods, because air just doesn't have the cooling capacity. Now, these are a few different lighting applications. The top couple are natural convection LED lighting applications. This is similar to what we will be looking at today. We do have customers using us for data center cooling as well. And medical equipment cooling is always an interesting one for me. Usually those end up being sealed enclosures due to medical guidelines. They can't have any openings. So whether it's natural convection around a box, external or internal, we can certainly model it. So I'd like to take a look at the use case for today. This is a passively cooled LED work light. This is something you might see, for instance, in a mining application where they have to light an area underground really 24/7 with high durability. These lights, for a number of reasons, do end up usually being cooled by natural convection. I guess, first of all, you don't want to have to rely on a fan. They can break. It adds expense to the system. And for something that needs to be on really all the time and have a long life, it is important to make this work via natural convection and at as low cost as possible. Here we have 6 individual LEDs on this assembly. The assembly is made of aluminum, of course. It's anti-corrosive, and we have 3 watts on each one of these LEDs, so it's a total of 18 watts. The main objective of running the simulation is I take a look at a couple different heat sink patterns here, and really I'm trying to answer the design question: how many fins do I need in here to get an optimal operating temperature on the chips? Do I need more fins? Does that result in a better performance? Of course, as you add fins, your material cost and manufacturing costs, machining costs go up. So we'll understand the sort of trade-offs between those options. So this is a conjugate heat transfer analysis. All that means is that there is solid conduction through the solids, of course, and there's convection around the model. These both have to be simulated at the same time, solved at the same time. Of course, the temperature causes that convection plume, so that's how a system like this works. It is steady state. Generally speaking, transient isn't really needed, right? These things need to stay on for a long time and work. If we're running into problems in the transient state, we're not going to be okay on the steady state analysis. Natural convection is pretty much always laminar flow, so I've set this up like that. And sort of the leading indicators to a good design or a bad design to me are looking at the junction temperature of the LEDs, as well as sort of understanding the flow or velocity over the heatsink fins. Here's an overview of the model in CAD. There's a front casing here. Again, the front casing and the back is aluminum. Of course, it's resistant to weather and is a pretty good conductor as well. There's a glass panel in the front. Behind that glass panel and front case is a rubber gasket. There is an internal volume, which is sort of interesting. So now we have an internal air volume over the chips, as well as a bounding box around the system. There's a PCB, of course, and the 6 chips. This is the design variant I'll be looking at today. So I'm varying the number of fins here. And my question is, of course, the 15 fin design is going to cost more money in material and machining, but I'm curious, does it perform better? Does it result in a lower chip temperature, LED temperature? The one thing to note in the electronics cooling world, of course, is the chip temperature. The life of the chip drops off significantly as a function of temperature. It's not linear. It really gets pretty nasty fast. So to have a long cycle life on your components, it's very critical to keep the temperatures low. So here are some results. I'm going to sort of dive into the results here, and then we can take a look at the why. On the left, we see, first of all, to start, these 2 have the same legend, right? So I capped the legend at 70 Celsius. And on the left, we have the 9-fin model, which is really showing a temperature around 52 degrees Celsius or so on the fins. It is sort of a teal, so it's cooler than the one on the right. And there is a gradient here. So if you sort of look there, sort of as expected in the center here, probably where you have a bit of a lower velocity, you have a higher temperature here. What's interesting is that consistency sort of in the center is patterned or is also seen in the 15 fin model. However, this is over 10 Celsius warmer on the right. So this was sort of non-intuitive to me a little bit at first. I figured increasing the surface area is always a win. However, we're going to sort of dive into the results and try to understand why this happened in a moment. Here's another way to visualize the data. So the red bars are temperature of the different all 6 chips for 9 fins. The blue is for 15 fins. Again, we're consistently seeing about 20 Celsius delta, which is really not something you want to you want to get as low as possible. So in the electronics world, 10C is a big difference. And so evaluating in just a couple hours that in understanding that the 9 fin design is superior is a big win. All right, so I'm going to dive into the results now and take a look at the SimScale project. So I tapped over here, and we are in the post-processor taking a look at some of the results for the 9 fin model. Now, I did hide the big sort of bounding box around the model. It's not too important. And just so you understand what we're looking at here, I've colored the solid assembly as temperature. So I'm mapping temperature to this. And I do have an ISO volume where I'm taking a look at velocity. So let me just sort of pause, and the model is in transparent, and I want to understand the temperature distribution over this. As expected, the chips are the warmest. The front has a warmer section sort of hanging towards the top, you'll notice. And the first question I had was, generally with a heatsink design, what does the flow distribution inside the heatsink fins look like? So I ended up adding a ISO volume, and I said, okay, show me everywhere that is between 15 centimeters per second velocity and higher. I know my maximum is about 65 centimeters per second. However, I just want to know a threshold where I have a good amount of air moving through this model. What sort of caught my eye first is looking straight on, there's good velocity distribution through all these channels. Now, you'll see 2 different things with heat sinks. Sometimes in the center, there's a lowest velocity because there's just blockage coming in from the sides, and it sort of chokes the flow. So you'll see a lower velocity. Sometimes that happens at the walls. I think the last space here is a wider distance out to the external casing. Regardless, if you look at where we hit this 15 meters per second or higher in the vertical direction, I'm really happy to see that this starts pretty much in the same place the whole way down. It'd be great if we could get a design where we have the high velocity come all the way down to the beginning of the heat sink. Again, gravity is down on this, so we're looking at it as if we're staring at it head on. Gravity is down, but it takes a minute to develop, or takes some distance to develop a thermal plume here. The next question I usually ask is how much of the heat sink is doing work here. So if I look at this sort of head on, what's actually very interesting is probably only about, let's say maybe 75%, 70% of the heat sink is probably really transferring heat. So what's going on here is we have this plume. There's a hot area in here by the chips. It's conducting out these fins, and the fins are causing a thermal plume, which is causing a velocity. Now, you'll notice the velocity is not above that 15 centimeters per second out towards the end of the fins. This means we could actually shorten up this heat sink quite a bit, probably, and get the same answer. So we could potentially save on material costs, and at this point, who knows, maybe I try a couple different fin designs or patterns. So now I like how this looks, and now I want to really understand how the 15 fin model looked. Really, when I add more surface area and add more fins and I get a hotter temperature, the first thing I do in simulation is kind of wonder, okay, is this physical? It's good to get the hard data, but you need to interrogate it yourself and understand if you're getting good results. Putting in an ISO volume that shows the same 15 centimeters per second or higher on the 15 fin design, we don't get any velocity which is above that threshold in the fin area. So what's going on here is we added so many fins that we just obstructed the flow, constricted it. It's too hard to promote flow in there, so it's just going around it, and that's what's causing our high temperatures. Once I saw this, it became very clear to me that the results were, of course, realistic. I just had sort of my preconceived notion was a little wrong here, that turning up the heat sink area would get you better results. Again, with this one, probably could shorten up the heat sink fins as well. So this is really what I wanted to show you for results. At this point, I would like to show you how to set up the model and really show you how in about 10 minutes you can set up a model for simulation. So the first step is to upload your CAD geometry. We support and work with really every major CAD vendor there is. All you have to do is select the plus icon here and drag and drop your geometry. There is no need to go to a CAD neutral format like STEP. We support all the major ones, so SolidWorks, Inventor, Creo, NX, and so on. We support those direct assemblies, and so a lot more of your data is preserved. This is my geometry I happen to import from Onshape. Behind the glass, you do see the PCB as well as the 6 chips. Before I actually run the simulation, I do need to do a couple CAD operations. So if you've done simulation before, you know that there needs to be a couple flow volumes here, as well as I need to do a surface split. I'm going to edit this in CAD mode. This is a new functionality that's supported in SimScale. We are now supporting basic CAD operations to just try to reduce the amount of times a user has to go back into CAD. It always is sort of a drag when you forget to tweak one thing and have to go back. So we're really trying to remove that friction. The first step I'll do is an internal flow volume. So all I have to do is select the seed face. Again, it's a completely enclosed area because this is a weatherproof box. I'll give this a moment to complete the internal flow volume. We see this is added to the history on the left. The next step would be an external flow volume, sometimes called a bounding box. And when I select an external flow volume here, we sort of size it, we sort of give an estimate for sizing. Now, there are best practices about how to size this. Ultimately, we don't want to constrict the flow or have the wall so close to the geometry that it causes problems. I usually go with, if we say one side of this is a length, I usually go with about 5 lengths below, 7 above, and 5 to each side. I did do this ahead of time, so I'm going to just punch in some lengths here. And this is looking a lot closer to what I think is appropriate. It doesn't hurt to always go a little larger, just adds a little more mesh. And I'll select a seed face. Great, I have my 2 flow volumes. The last step is just an imprint. If you forget this, sometimes it happens, we'll give you a warning. All this does is it splits surfaces which are touching. So really the accounting of the conduction heat transfer at the interface is done appropriately. At this point, I'm done. I'll select finish and we'll go back to the workbench. Okay, this is the geometry I just worked with. We come back and name it a copy. I usually actually like to just end this with a flow volume extraction tag. And now I'm ready to set up my simulation. This will be a conjugate heat transfer analysis, of course, like I mentioned earlier. I'm going to use this CHT V2 solver, and I'll select create simulation. Ultimately, my goal here is to work down through the tree. A green checkbox means you're all set. You can continue to the next step. A red circle means something needs to be addressed before, and ultimately, we're trying to get down to simulation runs to kick off a simulation. Here, I did mention this is laminar flow. I'm not going to worry about radiation for now, so I'll hit save. Now, under model is where you would define a gravity vector. This isn't required for, say, a force convection analysis, but because this flow is dependent on density, it is necessary to define the gravity vector. You'll notice the Cartesian coordinate system in the lower right corner with the view cube. Here, down is going to be in the minus y. So next I select air, and remember there are two fluid regions. There's that internal one as well. As I assign things, I usually like to sort of hide them for just accounting purposes. Next, I need to start working on the solids, starting with aluminum for the casing and the housing. This front panel is glass. And if I hide this, we have a gasket in here as well. So next we actually have to define the PCB. So I was mentioning earlier about how we do support anisotropic materials. What I'm going to do here is modify just a default material. So I used a plastic, and instead of a thermal conductivity, which is isotropic, I'm going to go with orthotropic. This allows you to define the thermal conductivity in the planes. And here, if we look at the view cube, we're going to have high thermal conductivity in the Y and X and low in the normal direction. Usually, depending on your board, this comes out to about 20 watts per meter K in the in plane. And then for the out of plane, it changes, but maybe it ends up being around 1. Lastly, I will apply a silicon to these chips. Great. Next, I have to do the boundary conditions. For a natural convection setup, we actually have what we named a natural convection inlet-outlet. All this means is it's just an ambient. In the background, we define a total pressure of 1 atmosphere, and here we just have an ambient temperature. So this is, it does follow electronics cooling guidelines or best practices. Pretty much, we're modeling this as if this assembly is just floating in a room. Lastly, we do have to define our heat loads. So down under advanced concepts, we have power sources. This is where you can list a wattage on a volume. And instead of using the viewer, I'm just going to click from the tree here, all 6 of my chips, and this will be 3 watts. This is 3 watts per volume, so we'll have 18 here. You'll notice at this point we have green checkboxes the whole way down the tree. I can go ahead and select run, and we give you a resource estimation. So we tell you it might take between 85 and 120 minutes. It will use 36 to 54 core hours, and we haven't even meshed it at this point. So we give a mesh estimation. Of course, if you generate a mesh first, it tends to make the resource estimation more accurate. But for now, I can go ahead and select start and kick off a simulation run. Now, one of the big advantages Yusuf touched on and differentiators compared to a desktop solution is you can run multiple simulations at once. So for instance, maybe I can try a more heavy duty, higher wattage load on my LEDs. I can change the boundary condition here, go down to run and kick off another simulation. So I think this would be 30 watts, run 1. And I can do as many of these changes and kick off as many of these simulations as I want. Of course, it is still waiting for that mesh there, but if I already had a mesh, I could kick off 10 or 20 different operating points. On a model like this, a lot of times you'll start stepping up the ambient temperature and understanding the delta increase between ambient and your chip temperature. If at any point you get stuck as a SimScale customer, we do have in-product chat in the lower right corner here. You can send us a message. We do staff this during business hours, and we will get a CFD engineer will get back to you and help you out. This is a much faster feedback loop than filing a support case in a ticket system, sending someone your files, and then waiting to get getting information back. As a commercial customer, all of your projects are completely private. However, you can actually check this share project with SimScale support at the bottom, and we will get temporary access to see your project. So maybe I'm running into a meshing error, and we can help you out in real time very quickly instead of having to wait days or maybe even a week to get some help.
Excellent, Matt. Great presentation.
Thank you. That's mostly what I had to share. I think I'll stay in product for a minute. If there's any questions, if it doesn't make sense, I'll stop sharing.
We have a couple of questions coming in, Matt, and I think the first one we could cover is how do I choose which machine to run the simulation on?
Sure, good question. So I skipped it because we sort of automate this type of stuff. But under simulation control, we're actually saying we're going to do 1,000 iterations. And here's where you can choose the number of processors. So we support on running up to 96 cores, which is a huge machine. But if you have some simulation experience, dividing up a small problem on 96 cores doesn't always make sense. So what we do is we mesh it, choose the machine that will get you the answer as soon as possible, the fastest runtime, and automatically kick it off on that machine.
Great. Second question would be, do I have to keep my browser open when the simulation is running?
Yeah, so that's the nice thing about SimScale, right? You don't have to do that. You can shut off your computer, close your browser, open it up on another computer. I've actually never had SimScale crash on me. I've never lost data on SimScale or anything like that. So those are sort of problems of the past, I would say.
Great. We have another question coming in. What mesh settings are recommended on a heatsink?
Yeah, that's a good question. So the main thing you're going to want to sort of look out for. So let's go ahead and take a look at the mesh settings. And let's just create a new mesh here so I'm not interrupting the one that's going on. Really what you need to be cognizant of is you need a lot of mesh density in between the fins where the fluid is, because that is solving your flow, and your flow is going to be what affects your chip temperature. So in other words, if your mesh is too coarse in here, or if it's not resolved well, your temperature is probably going to be over predicted. Now, there's one specific sort of tool which is very helpful for small channels like this. Down under the advanced settings, we have this gap refinement factor. And what this is it guarantees a number of core cells, even through the thinnest channels. Now, this doesn't count your boundary layers we have here. So let's sort of isolate. Let's pretend we're thinking about between this surface and this surface. If I set this value to, let's say, 2, we're going to have our 3 wall layers by default, or 3 boundary layers on this side, 3 on this side, and then we're going to have 2 core cells through the channel here. I think on the model I actually ran, I used 3 here, and you can get a lot of mesh density through this model. Now, I think I actually took a screenshot in the post processor. I should be able to pull it up. You can view your results through that channel. Perfect. So you could count, but we have at least 4 cells across the channel here, 4 core cells. I'm happy with this, and I know it's not affecting my results in a non-physical way.
Excellent explanation. Thanks, Matt. We have another question coming in. Is it possible to import personal settings from OpenFOAM and load them into SimScale for use?
So the answer there is no. We don't consider ourselves, just people sometimes throw around a GUI for OpenFOAM. We don't. That's not really what we're trying to get after. Although at times we have used OpenFOAM as the solver, we're just trying to make our own solution that is easy, that a mechanical design engineer who's designing electronics can get some reliable simulation results out of.
How do you model dust accumulation, which will negatively affect convective cooling?
Well, we can't explicitly model dust. There probably are some tricks. For instance, looking at particulate, I've sort of known where dust particle dropout velocity is, and so you can sort of use some tricks or hints, understanding if you know the velocity field and if you can treat it as air, you understand where things may accumulate or fall out. However, we do not explicitly model dust.
Hi, can we evaluate the U value in construction industry?
Sure. The answer there is yes. So what you're going to end up having is an assembly of a wall with your different materials. For instance, drywall, and then insulation, probably some wood studs. You could import that assembly. I've done it with Revit, and you can actually sort of assign a temperature delta across it and figure out how much heat transfer you have going through, and back calculate a U value.
Excellent. Then, if we also use particle trace for the evaluation.
Yeah, absolutely. So a particle trace is if you're just following a single particle through the system. So usually I put those at the inlet. In this model, I could put them, I didn't set it up for this one, but you could put that at the inlet where the air comes in. You could observe the particle traces going over the heat sink, and sort of what I showed you with that ISO volume would probably be confirmed as well. So not a lot of heat transfer going through the very end of the fins, and the 9 fin design is superior.
We have another question coming in regarding Monte Carlo simulation, if that's the principle that you used during your simulation process.
I have not used that for this analysis. I know some of our customers use this. This model was more just for demonstration purposes. But if I was doing consulting work or something like that, I might consider that.
Great. Also, we have another question. Can SimScale model forced convection? That means fans blowing on heat sinks, for example.
Absolutely, we sure can. So we support momentum sources to model forced convection. You can model the blade geometry explicitly. You can use boundary conditions, no problem at all. So we've got all the options. We can model forced convection.
Excellent. Thank you so much, Matt. If there are any more questions, make sure to put them in the question box. We'll give you around 1 more minute, and then we might wrap things up. We have another excellent question coming in, which asks, is there a way to measure mesh quality?
Yeah, and I guess I should not have jumped out of product. Let me go back in. So I ran this mesh, I guess a while ago. It was 6.5 million cells, and we have a meshing log here. And there's a lot of metrics, sort of your common metrics you would see in other solutions. For instance, the volume ratio. This is just the ratio between ratio of the volume between two adjacent cells. So the worst area in the model is one cell is 30 times larger than the one next to it. A lot of times there's a lot of metrics here. It's very helpful. However, it's easy to get overwhelmed, right? So I would say a lot of times, if you look at the worst metrics, they're all going to point to the same issue or problem. Here, the mesh quality was okay. I was happy with it. But for instance, if I looked at where the non-orthogonality was perhaps above 80, it would probably also show me where the volume ratio was 30. So that's usually how I tend to find it. We can also visualize where that is in the model as well. So it's very helpful.
Another question coming in is the PCB autotropic value critical?
Yes, it is. It's very important. The main, for a couple of reasons, right? So really what's going on here is that this is where the majority of the heat's going. And so because the chips are right onto the PCB, it's going to have a very large effect. If you change, if the thermal conductivity is inaccurate, it's going to have a very large effect on your temperatures.
Mm-hmm. I think that's it. We covered most of the questions. If there are no more questions, then I would like to thank you. Also, thank you, Matt, for the very, very nice presentation and demo. Really much appreciate it.
Sure. Thank you, Yusuf.
If you have any more questions, feel free to reach out either to Matt or to me, and the recording will be uploaded to our YouTube channel soon, and you will be able to watch the on-demand recording if necessary. So with that being said, thank you so much again. I wish you an awesome day or night from wherever you're watching right now.
Thank you, everyone.
Bye-bye.